All right, guys, well, welcome to your first virtual lesson for calculus. We're moving into a new unit, applications of derivatives. So now is when we're going to take what you learned in the last unit and look at how it's applied in the real world. So the first topic that we're going to talk about is velocity. And I know some of you have a physics background, so you're going to see some overlap for sure. Before we get into the velocity piece, just a reminder, when we were talking about derivatives are something that can represent a rate of change. And so we're going to focus on velocity, and then next lesson we'll get into acceleration, and then throughout the unit we'll look at other rates of change as well. So just as a refresher, velocity is the rate of change with respect to time. And remember that with respect to we'll use as WRT. So again, velocity is the rate of change with respect to time. So if we were looking at a function, and the function was s of t, s could represent displacement, and t could represent time. Just a side note, displacement is when we're talking about the change in position from the original position, and then if we're talking about distance, that's the total amount of space traveled. So you'll be looking at the difference between distance and displacement in this topic. So S of t represents displacement as a function of time. Okay, displacement as a function of time. So that's basically our S equals, or our position equals. The first derivative is going to represent the rate at which the displacement is changing with respect to time. So essentially, this is our velocity. So the first derivative of a position time graph would be velocity. And so we can write that as ds over t. So the derivative of displacement with respect to time is v. Now, if we take the second derivative, this is going to represent the rate at which the velocity is changing with respect to time. So essentially, we're talking about acceleration. Now, this can be written as the second derivative of position with respect to time, or the derivative of velocity with respect to time, and that would equal acceleration. So if we go back to some previous lessons, just a reminder that when we're talking about average velocity, this is going to be the slope of the secant line. Okay, so that would be the slope from point P to Q would be your position at time 2 minus your position at time 1 all over time 2 minus time 1. So again, that's basically your slope graph, y2 minus y1 over x2 minus x1, but we're writing it in terms of velocity and slope. Now, when we're looking at instantaneous velocity, this is when we're looking at the tangent. So m tangent, or m tan, is, if you go back to your limits, the limit as h approaches 0, we're using first principles, f of x plus h minus f of x all over h. So we break down everything that we've got there. If we're given s of t, that's our position. If we're given s prime of t, so the first derivative, that's velocity. And if we're given s double prime of t, so the second derivative, that's going to be acceleration. If any of that's something you need to go over again, pause the video, back it up, and then you can come forward to the next example. All right, so the first example here, we're just going to look at that, kind of review our derivatives. So we've got the displacement with respect to time of an object thrown off of a cliff in a downward direction is that formula there. Now it says determine the first and second derivatives of the function. So our first derivative would be the derivative of position with respect to time. And if you remember, we bring that 2 forward. So we've got negative 9.8t minus 9. If we look at the second derivative, we can write that as the second derivative of position with respect to time. We could also write it as the derivative of velocity with respect to time. And we would get negative 9.8. Now again, for those of you that have done physics, that number should look really familiar because negative 9.8 correlates to negative 9.81 meters per second squared, which is the acceleration due to gravity. So this is your A. Now, as a side note there, if we have questions that involve falling objects, we're going to assume that the ground has a displacement of 0 and all points above the ground are positive. When you get into college, into physics, there's going to be opportunities for you to change your change your polar points, and you could have up being negative and down being positive. But for the purposes of these questions, we're going to use displacement at 0 and all points above the ground are positive. All right, so let's talk about Super Dave. Super Dave jumps off the roof of the CN Tower. His height's given to you. His height above the ground in meters after t seconds is given by the formula. So the first question asks us to find his velocity at 2 seconds. So we're finding his velocity at 2 seconds. This is an instantaneous velocity. So it's going to be at exactly 2 seconds. And if we're finding his velocity at exactly 2 seconds, we're actually looking for that first derivative. So the velocity of the given time is going to be the derivative of the height. So velocity with respect to time is negative 9.8 t. So if we want to find the velocity at 2 seconds, velocity of 2 seconds is negative 9.8 times 2. So our velocity is negative 19.6 meters per second. Now, if we want to figure out the time at which Super Dave is going to hit the ground, we have to consider our speed. When we hit the ground, that's going to, or not, sorry, not our speed, but our height. When Super Dave hits the ground, his height above the ground is 0. So that's when h is going to equal 0. And we're talking about height, so that's going to be when is h of t equal to 0. So we're going to look back to our original formula. H of t equaled that 446.5 minus 4.9 t squared. And so if we substitute in 0 for h of t, we're looking for when 0 equals 446.5 minus 4.9 t squared. Okay, so solving the equation, we've got 4.9 t squared equals 446.5. We'll divide by 4.9. And we have t squared equals 91.122. And then we'll square root. And our time will equal plus or minus 9.55. So we need to look at the answer that we came to in the context of the question. We're not going to have a negative time, so we eliminate the negative, and time is 9.55 seconds. So 9.55 seconds after he jumps off that building, he's going to hit the ground. The next question asks then, what is his velocity when he hits the ground? Now again, with your physics people, we want to ignore terminal velocity right now. We're just thinking theoretically. What is his velocity when he hits the ground? So this time we're looking at velocity. So that means we're using the derivative. So v of t is negative 9.8 t. So we plug in the 9.55 seconds when he hits the ground. And negative 9.8 times 9.5 seconds is negative 93.55 meters per second. Not so good for Super Dave. Now, at any point, I'm going to have your notes uploaded as a PDF, so you could choose to try doing some of these questions on your own first, and then using the video to check. A rock is thrown vertically upward from the ground level. Its displacement d with respect to time is the formula given. And then it points out there that t is greater than or equal to 0. So our initial time is 0. So the first question says, determine the initial position of the rock. Well, the initial position of the rock is going to happen at the initial time, which is when t equals 0. So the position at time equals 0 is -5 times 0 squared plus 30 times 0, which is 0 meters. So the initial position is 0 meters. If we're asked to determine the displacement of the rock from 1 second to 4 seconds, we're looking at that time interval of 1 to 4 inclusive. So our displacement is going to be our position at time equals 4 minus our position at time equals 1. So subbing in our values, we're going to get 40 minus 25, which is 15 meters. So the displacement between time 1 second and time 4 seconds is 15 meters. If we're asked for the average velocity, if you go back to the first page of your notes, if we're asked for the average velocity from 1 second to 4 seconds, we're basically looking at that slope formula. So the average velocity is the change in displacement over the change in time. So the position at time 4 minus the position at time 1, all divided by time 2 minus time 1. So we've already figured out that S4 minus S1 is 15 meters. And 15 meters over 4 seconds minus 1 second is 5 meters per second. So our average velocity between those two time points is 5 meters per second. But if we're asked to determine the velocity after 4 seconds, then we're looking for an instantaneous velocity. The instantaneous velocity would mean looking for the velocity at exactly 4 seconds. So this is instantaneous. And in this case, we're looking at the derivative. So our velocity will be the derivative of the position with respect to time. The derivative is -10t plus 30. And so if we're looking for the derivative at exactly 4 seconds, we can write it as v of 4, or we can write it as the derivative of position with respect to time when t equals 4. We'd have -10 times 4 plus 30, so -10 meters per second. So that would mean that the rock, with the negative, is going to tell us that the rock is moving down. So our negative velocity here is going to tell us the direction that that rock is moving, and that rock is moving down. The question then is, when does the rock reach its maximum height? Well, when is a time question. So when does the rock reach its maximum height? That's a time question. And its maximum height is going to happen when the velocity equals 0. So the rock's going to go up in the air, and then it's going to come back down. And at this point here, its maximum height is when the velocity is going to equal 0. Again, if you've taken physics, this is something that should be familiar. So we're going to let our derivative equal 0 and solve for time. And then the final question asks, what is the rock's maximum height? So in this case, we're being asked, what is the rock's maximum height? And what is going to be our displacement? So it's going to be important that when you're reading your questions, you're looking at whether you're being asked for a position or whether you're being asked for velocity. And if you're being asked for time, is the piece that you're given velocity or position? So in this case, you're being asked, what is the rock's maximum height? We know the maximum height happens at time equals 3 seconds. The displacement would be s of 3 equals -5 times 3 squared plus 30 times 3. Notice we're using the position formula this time because we're being asked for position, not velocity. Again, if at any point you need to go back and review some of these questions, please do. Just pause the video, back it up, and then come back to the next example. So the final example, we're going to put it all together and then look at what that looks like on a number line for this particular example. So a particle is moving along a line and its position is given by that formula. T again is greater than or equal to 0. We're being asked to find the average velocity from t equals 2 seconds to t equals 4 seconds. Again, average velocity, we're looking at the slope formula. So average velocity is the change in position over the change in time. So off to the side, I'll figure out what those positions are. So at time 4, our position will be 32. And at time 2, our position will be 52. So we'll use those numbers in our formula. At time 4, it's 32. At time 2, it's 52. And 4 minus 2 is 2. So our average velocity is negative 10 meters per second. Now, if we want to find the velocity at any point in time, then we're looking at instantaneous velocity. Which again is the derivative. So velocity is going to be the derivative of position with respect to time, giving us 6t squared minus 42t plus 60. If we're asked to find the velocity at a particular time, then we're just subbing in that point for t. Now, I can write velocity of time equals 6, or I could write velocity equals the derivative of position with respect to time when t equals 6. So either one of these examples can be used when we're representing derivative. All right, so we sub it in. 6 times 6 squared minus 42 times 6 plus 60 equals 24 meters per second. Again, all of these are just applications of the derivative. This particular one, we're going to go a little bit further and actually map out the movement of the particle on a number line. So when is the particle at rest? The particle will be at rest when the velocity is 0. So we're going to figure out when is the velocity at 0. So our velocity, again, was 6t squared minus 42t plus 60. So we sub in 0. And in this case, we have to factor. So we'll start by pulling out a common factor. Pull out 6. We've got t squared minus 7t plus 10. And our numbers that multiply to be 10 and add to be 7 are 5 and 2. And we need them to be negative. So my factors can be 6 times t minus 5 times t minus 2. Meaning that t equals 5 seconds and t equals 2 seconds. So these are the points when the particle will be at rest. Once we know when the points are at rest, we can then start figuring out when the particle is moving in a positive direction or a negative direction, and from that point we can actually map the movement of the particle. So we know from our points above that the particle is at rest when time is 2 seconds and time is 5 seconds. So it stopped at 2 seconds and it stopped at 5 seconds. We also know that the particle will be moving in a positive direction when our velocity is greater than 0. So the way that we're going to figure this out, we're going to do it in 3 steps. First step, we're going to figure out our critical numbers. Now those critical numbers can be your NPVs or your zeros. In this case, we're just dealing with zeros. We've got NPVs or your zeros. So we've already figured out our critical numbers in the last question. Then we're going to set things up on a number line to just give us a general visual of what's happening. And then we'll create an interval chart. So the first thing is our critical numbers. We already know that the critical numbers are 2 and 5. From there, we're going to create a number line. So we've got 0 seconds, 2 seconds, and 5 seconds. Those are our critical numbers. And we're going to look at what's happening to the particle during those points. So if we go from 0 to 2 seconds, we can actually sub in, any value that's between 0 and 2. So for example, 6 times 1 squared minus 42 times 1 plus 60. We can sub that in and we'll find out that this is moving in a positive direction. We can sub in for the next one here. We can sub in, I used 3. So 6 times 3 squared minus 42 times 3 plus 60. This is going in a negative direction. And then for the next one here, I could sub things in and it would be going into a positive direction. And so I chose to sub in 6. Now, you don't necessarily have to do that substitution. You can get the information from an interval chart as well. So if we do our interval chart, our critical numbers were 2 and 5. So we're going to set up our intervals from there. Our factors were t minus 5 and t minus 2. And then we have our velocity. So if we go back to our original question, our original formula, once it was factored, we had 6 times t minus 5 times t minus 2. That's what our velocity is. So our velocity was 6 times t minus 5 times t minus 2. Our critical points happened between 0 and 2 because time was greater than or equal to 0. And then between 2 and 5. Notice the round brackets because we can't include the 2 because at 2 the particle is at rest. And then the last interval happens from 5 to infinity because it's going beyond the 5. And again, round brackets. So we sub into each of our factors. I'm going to choose numbers that are between 0 and 2 and 2 and 5 and so on. So my test numbers, I chose to use 1 and 3 and 6. And so if I plug in a 1, t minus 5, 1 minus 5 is negative 4. So this is negative. And t minus 2, 1 minus 2 is negative 1. So that point is negative. If we look at our original equation, we're going 6 times t minus 5 times t minus 2. Well, a negative times a negative is a positive, so the velocity will be positive at that point. And if you notice back up here, that's going in a positive direction from 0 to 2. T minus 5, 3 minus 5 is negative. 3 minus 2 is positive. And a negative times a positive is negative. So the particle is moving in a negative direction. From 5 to infinity, I use 6. 6 minus 5 is positive. 6 minus 2 is positive. And a positive times a positive is a positive. So the particle is moving in the positive direction. So you could just write out your basic number line do your interval chart, and then go back to drawing out those points. So if we were writing down when the graph is going in a positive direction would be from 0 to 2. Notice the signs. And when t is greater than 5. If you wanted to write this using set notation, it would look like this. Or, sorry, interval notation. We looked at when the graph was going in a negative direction. The graph is going in a negative direction between time equals 2 and time equals 5. Again, we're not using the equal to's in our inequalities, so it's when time is greater than 2 and less than 5. There's no equal to signs because that's when the particle's at rest. I'm using this using interval notation, it would be 2, 5. Now we can take this information and sketch what the particle movement actually looks like. So we want to sketch the motion of the particle. The first thing we're going to do is go through and figure out everything that we know. So summarize everything that you know or that you can find easily. So we know that the particle is at rest at time equals 2 and time equals 5. So those are going to be turning points. And we know from our chart from the last page that the particle changed directions at those points. So turns at time equals 2 and time equals 5. That's when our velocity, so the derivative of the position, that's when our velocity is equal to 0. We know that the particle is moving to the right between 0 to 2, meaning it has a positive velocity. It's moving to the left between points 2 and 5, so that would mean it has a negative velocity. And it's moving to the right again as the particle is greater than 5. And again, positive velocity. We also can figure out the positions of the particle at some key points. So the position at time equals 0, 2, and 5. So at position 0, or at time 0, the position is 0 meters. At time 2, the position was at 52 meters. And at time 5, the position was at 25 meters. So using all of that information, we can actually sketch the position of the particle. So we'll start by drawing out a number line. And then we start plotting our key points. So we know at time equals 0, our position is 0. We know that at time 2 seconds, the position is at 52. And then we know that the particle turns, and at 5 seconds, the position is at 25 meters. So the particle moves towards 52 meters. And then at time 2 seconds, the particle turns. And then at 5 seconds, the particle turns again. So that would be a sketch of what our particle movement is doing. And again, you can use arrows to show direction. So from there, you can figure out two different things. You can figure out your displacement, how far is it from the original point, if it had actually stopped. So for example, with the next question, you're going to be asked about total distance. If we're asked for total displacement at 6 seconds, then we would find out where was the position at 6 seconds, and that subtracted by 0 would tell us the displacement. But if we want to find the total distance the particle has traveled, we need to add up all of the movement. And so we figure out the movement between the intervals, and then we combine them. So when the particle is moving from 0 seconds to 2 seconds, that's going to be the position at time equals 2 minus the position at time equals 0. Because we're totaling our distance, we're just looking at the absolute value. It doesn't matter what direction the particle is moving, it's just how far did it move between those points. So 52 minus 0 is 52. Between times 2 and 5, it's going to be the position at time equals 5 minus the position at time equals 2. And again, it's an absolute value because we're just looking at the amount of movement, not the position of movement. So 25 minus 52 is negative 27, so that's 27. And the amount moved between 5 seconds to 6 seconds. So off to the side, you're going to figure out what the position is at 6 seconds. So if we were asking for displacement at 6 seconds, the answer would be 36 meters. But we're asking for distance traveled. So our position at 6 seconds minus our position at 5 seconds is 36 minus 25, which is 11. And when we total up the movement between each interval, we get 90 meters. If you have any questions about the lesson, go back and review the examples again. Feel free to reach out to me and ask questions if you have them. Your assignment is going to be page 124. It's going to be page 124, numbers 1, 2, 4, 6, and 7. So remember, you're watching the lesson outside of class, and you're using class time to work on the questions, but feel free to work ahead if you'd like to. Thanks, and see you next lesson.